Hello and good day to you. So today we're looking at logistic regression. If you want to follow along, you will need to go on Kaggle and get the HR Analytics case study. This is tagline: the Employee Attrition Analysis Logistic Regression Model. So that's what we're going to do with this. We're going to use this HR data set as a way of predicting if a given employee is going to leave the company with this data. And now, to give an explanation of what I mean by a logistic regression, you need to think about it as, so far we've done regression which gave a number, so usually it was money based or the like, but a logistic regression is risk based, or the percentage chance of a given classifier being applied. So to explain it in more detail, you might use this to create a medical model to show the likelihood of a positive response to a treatment given what you know about the patient. In the financial world, you might use it as a chance of defaulting on a loan given the subset of information you know about the customer. In the engineering world, based on a set of operating conditions, you might work out the chance that an item will fail or break in a given year, and then use that to budget or work out how much money you need to pay on maintenance. All the above sounds about probability and risk, but it can also be the probability that it belongs to a conceptual classification, hence why we talk about classifier. Now, the reason it's called logistic regression is it uses this logistic function, also known as the sigmoid function. And what the sigmoid function does is it takes the output from your regression, which is, apart from a set of derivatives that changes the way it's trained, exactly the same as the way you think about your linear regression, and then transforms it into this slightly more serpentine, non-straight value, which is between 0 and 1. Sigmoid function uses Euler's number, which is considered one of the most beautiful numbers in mathematics, and if you don't know what I mean by that, it's worth possibly looking up, because it has a whole load to do with recursion in statistics and is all over the place in nature. But you can see why, if there is recursion going on in your statistics, i.e. nobody goes from, if this was a straight line, you would get to 100% chance of something happening too quickly compared to the real world. There's a nice curve that happens in real statistical probabilities. So the sigmoid function just does this very nicely and introduces that nice curve into your risk analysis. So what we've done here, I've made a model ahead of time. Here's the one I made earlier. And to make it into a logistic regression, you use family, binomial, link, logit, as you can see here. And use a GLM function, not the standard LM function. Now, if you do the summary model, you can see this looks almost identical for your standard linear regression, and for our purposes and the way you might want to think about it, it is the same. And you can see here we're using data, age, job level, monthly income, percentage salary hike, and stock option level. You can see these are all minus numbers apart from percentile salary hike. And there's an interesting study around that people only ask for salary hikes when they're unhappy and planning to leave anyway. And usually if they've asked for a salary hike, they've already started looking on the job market. So there's a good chance that they've already found something and they're just asking because they're unhappy. So interesting And you wouldn't think of it like that, but there's a huge correlation between asking for salary rise and somebody's already planning to leave, which causes this here, which, funny. As you can see, they're very small numbers, very small changes. And you might look at that and say, well, that's all very well and good. Use it in the same way, use a regression, linear regression, you use the predict function, and you can pull out a prediction for your given data. The sigmoid function will make it into this wavy line, which makes it more naturalistic. Though you can imagine that you can't use R-squared methods as a way to value whether a classifier is working well or not. So with logistic regression, you use the ROCR curve, which was invented during World War II for radar. And what they did was they worked out the chance of given the sensitivity of their given radar, the radar that they got, at what level do they maximize their sensitivity, and what sense do they maximize the true positive versus false positive? So I'm going to have to put in a set of commands, and it produces this ROCR curve. Now, in a perfect world, I'd like that higher, but you get this idea of area under curve as a evaluation of how accurate your logistic regression is. If this was around 80%, that would be really good. It's not. But if you think about a random chance would be 0.25, because you've got true positive, the rate that I decide that a employee is going to leave and I'm right, or the chance that I say they're not going to leave and I'm right, versus the false positive rate. Now, as you can see, what's going on here is, like I said about the radar, this ROCR curve is increasing its sensitivity. It's starting at, that it's not going to differentiate, and it's saying, well, if I'm 99% sure, I'll treat it as true. Then and then it'll go 80%, 70%, and this gives you the sensitivity of your model and how much of the variance and chaos is captured in your model, in your classifier. Well, because if you think about it, because you've already introduced this nice curve, sigmoid function, and true and false binaries don't really work well with R-squared methods, this is really the only way of capturing that information of how good one model is versus the other. So, as you can see here, we use a predict to predict the model, which basically takes our model and applies it to our data as we've already got it, and then feeds it out into this plot at the end. Now, if I was to cycle back and change this model and drop information in and out, I could repeatedly retest and see whether I get an increase in the area under the curve. And the other use for the ROCR plot like this is, if I saw this line go up really quickly and plateau here, that would be a great model. But if I saw that it plateaus here, it might change how sensitive I believe I should make this model. So what this data outputs is it will output a value between 0 and 1, which will be analogous to the percentage chance of a given classifier being true. And that's fine for risk analysis, where what I want is just a risk of bad event happening. But when I want to know risk of it belonging to a classifier, this is much more in detailed and much more useful. And you can use this for other classifiers, but you'll sort of find it brought up as soon as you get into logistic regression. So that's logistic regression. Essentially, linear regression model, everything that applied to linear regression also applies to logistic models, with the difference that you do this transformation on the end output that you get. And if you see here, you've got this family function in your data, and you can, I believe there's a couple of different transformations you can apply to get different generalized linear models with different outputs. And these types of transformation functions are something you start to learn if you then look into neural networks, and you could see why lots of data doesn't necessarily follow the nice linear models we've talked about in linear regression. So I hope that's been of some use. Thanks. Have a good night. Bye.